Hello there, Mr. Sutton here, bringing you the AB Calculus 4-8 Extra Practice Number 2 solutions on mean value theorem. For this problem, I'm given the f function as cosine of x squared plus x plus 2, and I'm also given f prime. I want to know what value c satisfies the conclusion of the mean value theorem applied to f on the interval 1 to 2. Alright, so here's where you need to know what the mean value theorem actually says. It says that if we have a differentiable function on the open interval and a continuous function on the closed interval, then there is some c value on this interval where the instantaneous rate of change, in other words, f prime of c, equals the average rate of change, in other words, f of 2 minus f of 1 over 2 minus 1. So it is worth noting on this problem, since we are talking mean value theorem, that the conditions of the mean value theorem are met. We have functions that are a function, the function that counts here is the f function. It's continuous for sure. We know that cosine is known to be continuous, as is the polynomial that's inside of cosine. And we also know that you can keep taking derivatives of cosines and polynomials until the cows come home. So it's continuous and differentiable. But they're not asking about, can we use the mean value theorem? They're just asking for the c value that actually satisfies the conclusion. So we essentially just have to solve for the c value that makes this true. To do that, we are going to use the calculator. So let's go to that now. So here we are on my calculator, where I've been very busy off camera entering a few things. The first thing I entered in the y1 of my y equals is this cosine function, because I'm going to need to use the f function. Now the next thing I entered was basically what I have here, the average rate of change of f over the interval from 1 to 2. So I did alpha y equals to get the fraction form, and then I did alpha trace to pull up my y1. So I've got basically f of 2 minus f of 1 over 2 minus 1. And since they told me what the f function does in terms of showing work, I don't need to really show this thing applied or plugged in. I can just say f of 2 and they know what I mean here because I'm just using it once. Now down here in y3, I've got my derivative. That's this f prime right here that they gave me. And what I essentially want to do is figure out where y2, the average rate of change, which is going to be a constant, intersects y3. So I'm going to deselect y1 because that was the original function. I don't really care about that directly. And now I'm just going to graph these two. Now I need a window for this. I'm going to use the interval from 1 to 2 because that's the interval that we're trying to apply the mean value theorem on. So let me go to window, and let me go 1 to 2. And let me do zoom 3, or zoom 0 rather, zoom fit. And let's see what we're looking at here. So it's taken a while to think about this. We're asking it to do a lot of calculations. This average rate of change, for example, it has to recalculate f of 2 minus f of 1 over 2 minus 1 every single time. But whatever, it can do it. And here's the f prime that we're graphing. So we see that there is one value on this interval that actually satisfies this. Now you might notice there's this intersecting spot over here as well, but that's not going to count because the conclusion of the mean value theorem doesn't take into account endpoints. That looks like an endpoint. So let's do second trace, intersect actually, option 5. And let's just do enter, enter, enter near that intersection. And we get about 1.438 if we round that off. So that's going to be c equals about 1.438, which is going to give me choice B. For this problem, f is this x squared minus 9 over sine of x function on the closed interval 0 to 5. And we want to know on which of these intervals for this function can we apply the mean value theorem. So the mean value theorem can be applied if you are continuous on a closed interval and differentiable on an open interval. So basically we want to know if these intervals are in fact continuous and differentiable on the intervals that they say they are. So for that we're going to look at the function and see if we can figure out where this function is not continuous or not differentiable. This function, I mean, the numerator doesn't really have any issues. It's a polynomial. The denominator by itself doesn't have any issues because it's a trig function, or a sine function specifically, which is known to be continuous and differentiable. However, if the denominator equals 0, then we're in trouble. So we're going to have discontinuities for the original function wherever sine of x equals 0. And there's an infinite number of spots where that happens. The relevant ones, though, on the interval from 0 to 5 are going to be at x equals 0 and also at 180 degrees at x equals pi. And we could keep going, 2 pi, though, and all of those are beyond 5. So f prime also is going to have some issues there. If you use the quotient rule to take the derivative, without actually doing that process, you probably realize that you're going to have the denominator squared through that process. So with the quotient rule, f prime is also going to have discontinuities at 0 and pi because you're going to have a sine squared of x, which is going to have the same issues if you have something that makes sine 0. So given this, discontinuities at 0 and pi for both the continuity piece of this and the differentiability piece, which of these intervals actually makes sense? So interval 1 is from 1 to 3, and 0 and pi are not on that interval. Since there are no discontinuities on the interval, the mean value theorem can be used for 1 to 3. For 4 to 5, we also don't have 0 or pi on that interval. So because there's no discontinuities on that one either, that also works with the MVT. Now for interval 3, 1 to 4, we don't have 0 on that interval, but we do have pi, 3.14 and some change. Because we have a discontinuity at pi on that interval, we cannot use the mean value theorem for that one. So that means it's only going to be options 1 and 2, which is answer choice C. On this problem, we have a figure above showing the graph of a differentiable function between 1 and 5. Which of the following could be the x-coordinate of a point where the tangent line is parallel to the secant line through the points 1, f of 1 and 5, f of 5? So first off, we've got all these different x values, and also there is no such point is an option. So maybe we should ask ourselves, is it even possible that this x value exists? So when we're asking about the tangent line matching the secant line, we're pretty much talking about instantaneous rate of change versus average rate of change. That's what a secant line is giving us. And this is talking about the mean value theorem. Since we have a differentiable function, the mean value theorem is going to apply here, which means that we are guaranteed that f prime of c, the slope of some tangent line somewhere on this interval, is going to match the average rate of change between -1 and +5. We're guaranteed that there's a tangent line that matches the secant line. So that eliminates choice E, and now we can start looking to see which x value gives us that tangent line. So to help us out here, let's go ahead and draw the tangent line. We don't actually have any y values, so this is going to be a very visual look at things here. Our tangent line is going from 1 to 5 here. So we're trying to find, or our secant line is going there rather, so we're trying to find a tangent line that matches this secant line. Okay, well, let's look at our options. So R, right here, here's our horizontal tangent line there, and W, those tangent lines, those aren't even positive. The secant line at least has a positive slope, so we can very quickly eliminate R and W, choices A and D. So that means it's down to either choice B or C, T or U. Let's look at choice T. That's just the next one. That one, if we draw the tangent line, is going to be too steep. Here's the tangent line, this little greenish line there, clearly much steeper than the secant line. Let's take a look at U now, just to be on the safe side. Here's the tangent line at U. That tangent line looks a lot closer to this secant line slope than this other tangent line we drew. So U is going to be our best answer, letting us pick answer choice C. For this problem, f is this function here, this polynomial function. We want to know at what x value in the closed interval from 0 to 5 does the IROC of f equal the average rate of change of f over that interval. Now, this kind of sounds like the mean value theorem, but it's a little bit different. If this were truly the mean value theorem, we wouldn't be allowed to use the endpoints 0 and 5 as possible answers, because mean value theorem's conclusion involves an open interval. But they never said mean value theorem, so we actually could have 0 or 5 as answers for this one. All right, so let's keep going here. We need to find the average rate of change for this. So we're going to be doing f of 5 minus f of 0 over 5 minus 0. And this is going to be a fair amount of mental arithmetic here. You could do it out on paper. So for f of 5, we've got 125 minus, this is going to be 50, so that's 75 so far, plus 25 brings us to 100, minus 16 brings us to 84. So we've got 84 minus, if you plug 0 in, everything with an x is gone and you just have negative 16. So this is 84 minus negative 16, or plus 16, over 5. So that is going to be 100 over 5, which conveniently comes out to 20. All right. So we're trying to figure out at what x value does the instantaneous rate of change equal this average rate of change of 20. So next we need to find f prime. That's going to be 3x squared minus 4x plus 5. And we're setting that equal to 20 and solving. Well, to solve this, we've got a lot of things we could use. It's a no calculator question, so you need to use some kind of quadratic math. Either way, you're probably going to end up subtracting 20 over here to get negative 15. To zero this thing out, and now you either use quadratic formula or you to solve it by factoring. I went the factoring route, so we've only got two things that can multiply to give us 3x squared, 3x and x, and for 15 we've got the possibilities of 1 and 15 or 3 and 5. I'm just going to randomly test one of these possibilities. So I've got 3x plus 5 and x minus 3, and there's other combinations we could have done. If I multiply this out, that's going to be negative 9x, and then I'll have a 5x to go with that, giving me the negative 4x in the middle. So this actually works out. Hey, I was lucky on my first try. Good for me. So now setting these equal to 0 and solving, we've got minus 5 over 3 and positive 3 as answers. Now they said the interval was from 0 to 5. So that means that negative 5/3 doesn't count. It's only the 3 we're interested in, giving us answer choice D. For number 11, we have a pot of tea cooling, and the temperature is modeled by some differentiable function whose values are listed in this table. So based off of all this, we want to use the data to approximate the rate at which the temperature of the tea is changing at time 3.5. And of course 3.5 isn't even a value in here, but it doesn't need to be. Since this is a differentiable function, we can try approximating the instantaneous rate of change at 3.5 by finding the average rate of change over the interval that 3.5 is contained in. So the best interval to use, I would think, would be from 2 to 5. That's the closest to 3.5. So let's find the AROC between those values. So I'm showing what I'm doing here. Average rate of change equals h of 5 minus h of 2 over 5 minus 2. And I actually have to plug in numbers for h of 5 and h of 2. So that's going to be 52 minus 60 over 5 minus 2, which down there is 3. You could put the units of measure on at this point without simplifying it further and you'd be done. Or you can make this negative 8 over 3. The units is going to be the output units, degrees Celsius, per the input units, minutes. So we have negative 8/3 degrees Celsius per minute. For number 12, we've got a continuous function on the interval from negative 4 to 3. It's given in this graph here. And they told us we've got 2 quarter circles and a line segment, and this craziness about g of x equaling some stuff, which doesn't get used in this part of the problem, but did get used in earlier parts. So for this part of the problem, they want us to find the average rate of change on the interval. So let's start by doing that. So we have f of 3 minus f of negative 4 over 3 minus negative 4. F of 3 is negative 3. F of negative 4 is negative 1. So we have then negative 3 minus negative 1, so plus 1, all over 3 plus 4, which is 7. Grand total of negative 2 over 7, but you didn't actually need to simplify that. So now the next part of the question, they said there is no point between negative 4 and 3
for which f prime of c is equal to the average rate of change. Explain why this does not contradict the mean value theorem. Well, the mean value theorem says that at some point on this interval, the average rate of change, which is negative 2/7, should equal the instantaneous rate of change if the function is differentiable. The MVT requires this differentiability in order to actually apply. This function, if you look at this, is not differentiable everywhere. At 0, we have a corner. So since we are not differentiable at that spot, the MVT does not guarantee anything across this whole interval. Now, for smaller parts of this, maybe, but certainly not across this whole interval. So this is why there's no contradiction.
For this problem, we have some concert tickets on sale at noon, and they were sold out in 9 hours. Number of people waiting in line is modeled by some twice differentiable function L. Values of L are shown in this table up here. So on the top, we have all the hours. On the bottom, we have the number of people waiting in line at each of those specific points in time. And we don't know a whole lot about what happens in between. So we want to use the data to estimate the rate of change people in line or waiting is changing at 5:30, which is time 5.5, which is somewhere in this interval here. And then show computations and indicate units of measure. Okay, well, if we're just being asked to estimate a rate of change, an instantaneous rate of change, we can always do that with an average rate of change. We just have to make sure we use AROC on an interval that includes 5.5. So there's a whole lot of intervals you could use on this one, but probably the most sensical one to use is the smallest interval from 4 to 7. So I'm going to estimate IROC with an AROC of, this is going to be L of 7 minus L of 4 over 7 minus 4. So that's 150 minus 126 over 7 minus 4. And you don't have to reduce this at all, but if you wanted to, this is 24 over 3, which is 8. The important part, though, is you do have to include those units of measure. So if we're talking about the rate at which people in line is changing, this is going to be, let's see, we're doing L of t over t, so that's basically people per hour. So 8 people per hour. For this problem, we're trying to find out between time 0 and 9, the fewest number of times L prime must equal 0, and then give a reason for the answer. So figuring out the answer, the number of times, isn't too bad. It's the explanation that can get a little tricky here. So the way I'm attacking this one is I'm looking for sign changes in L prime, which is to say in my graph, in my table, I'm looking for places where L is going from increasing to decreasing or decreasing to increasing. Intuitively, if we look here, we're increasing from 0 to 1 and from 1 to 3, but then from 3 to 4, we're decreasing. So we go from increasing here to decreasing over here, which means that we must have turned around somewhere, which intuitively means we probably have an L prime of 0 somewhere in there. And then, after going to decreasing, from increasing to decreasing, we're increasing again to get to 150. Then we're decreasing after that to get to 80. So we have a function that appears to be turning around at least 3 times. So probably 3 is a good answer for this. But we have to justify that answer. And we have to be careful about doing this. So if I'm talking about sign changes in L prime, I have to be sure that those sign changes really mean that I passed through 0 for the L prime. Because you can have a sign change in L prime. You can go from one side of the x-axis to the other with a discontinuity as well for some functions. So how do we know that sign changes in L prime, which is what we're relying on with this increasing-decreasing argument, how do we know a sign change means we went through 0? Well, we know that because this is a twice differentiable function L. So that means that L prime itself is differentiable, which means there's no discontinuities allowing us to warp from one side of the x-axis to the other. So here's how I explain this. Since L of t is twice differentiable, any sign change in L prime of t signifies that L prime of t equals 0 at the spot where the sign changes. And then the rest of it is just tying together this increasing-decreasing argument. So I justified that by saying, since L prime changes signs 3 times at t equals 3, 4, and 7, L of t changes from increasing to decreasing or vice versa. That's how we know there was a sign change in L prime. Since this happens 3 times, L prime of t must equal 0 3 times. On this problem, we have a real-life problem involving a zoo and a contest to name an elephant. People are putting entries in some box, and this is the number of entries in the box at any given time between 0 and 8 o'clock p.m. All right, so we've got data in a table. We want to approximate the rate in hundreds of entries per hour at which entries are being deposited at time 6. So basically, they're asking us to approximate E prime of 6 by using this table. Well, the only way we can really do that is with the average rate of change. So we're just going to pick an interval that includes the time 6, like 5 to 7, and find a rock for that interval. So we've got E of 7 minus E of 5 over 7 minus 5. So 21 minus 13 over 7 minus 5. And you could leave it like this and not simplify it as long as you put some units on the end. But if you want to simplify it, that's 8 over 2, which is 4. And this is hundreds of entries. So this would be 400 entries over the time unit hours.